Okay, welcome in this session about asynchronous programming with C++ on Universal Windows Platform. My name is Eric Mitlet. I'm Program Manager on C++. Let me introduce Gor Nishanov, Software Engineer in C++ Group, and Peter Tor, Program Manager on Windows. Today we are going to talk about asynchronous programming, but before, I want to introduce you some C++ improvement in this last version. So now from Visual Studio 2015, you can target iOS and Android with the multi-device development. We're still working on the standard conformance, and we are proud to announce that we are feature complete for libraries for C++ 17, and still working on C++ 11 and C++ 14. The last one of the year is C-Clang C2 front-end support. That means if you have Clang code building with Clang LVM compiler, you can now use our front-end Clang and our back-end C2 to produce Windows code with that. We're still working on performance because performance matters when you do C++, on code generation and the speed of the compilation process. Better ID support. Refactor. So extract function, rename function, and we have an improved IntelliSense for large file and of course templates. And as we spend a lot of time debugging in C++ code, we are introduced new visualization, memory diagnostic, and graphic diagnostic. If you want to follow the life of one pixel, you have the tool for that. But back to our main subject about asynchronous programming with WinRT, and I'll let Peter introduce the subject.
Thanks, Eric. So, as Eric just mentioned, there are a ton of improvements in Visual C++ that you can use in your universal Windows applications and also in your classic Windows applications, your desktop or console applications. But if you're a Windows runtime programmer, one of the most exciting things with Visual C++ is better support for asynchronous programming. Now, if you have done any programming with C++ and the Windows runtime, you'll know that there are a lot of asynchronous APIs. In fact, there are over 1,300 asynchronous APIs in the Windows runtime type system. And the reason that we have so many of these is that we have a general philosophy about approaching APIs, which is if a method is going to take more than, say, 50 milliseconds to execute because it has to hit the disk or it has to hit the network or something like that, we want to make it asynchronous and push the work off onto a background thread or sometimes a background process so that we don't interrupt the user interface thread and so the application remains responsive and the user can still scroll or they can still see your spinning wheel saying you've got progress and so on. Now, of course, the benefit of this is that for our end customers, they get more responsive applications. And a universal Windows app is not going to become ghosted like a classic Windows app because the UI thread is being hung, because all the hard work is being done on a background thread. But the hard part about that for us as developers is that using asynchronous APIs from C++ can be a little bit cumbersome. And anyone that's done it will know what I'm talking about. But for those of you who haven't done it yet, I'm going to start off with a demo showing you how to simply pick a JPEG and show it into an app. And then later on, Eric will show you how we're making that better in Visual C++ with this time around. So at this point, I'm going to switch to Visual Studio, and I'm just going to run the application first, just so we can see what it does. It's a very simple application. I click on a button here that says Pick Image. I go and pick an image here. This is an image of Kenny Kerr. He's a most recent member of our development team in the Windows C++ team.
Hi, Kenny.
and that's all this app does. Very simple. Pick an image, show it in an image box. So we'll close that down. And let's look at the code for this today. So very briefly, we create a file open picker, which is a standard Windows type. We try to pick a single file. And then if we read the code logically, what happens next is we check if the user picked a file. If they picked a file, we open it. Then we display a bitmap, and that's how it gets onto the screen. And then you would imagine, thinking logically, that first of all, we're going to print this first one saying end of lambda. Then we're going to print this second thing that says end of second lambda. And then finally, we'll print this thing that says end of function. That's how you'd expect it to run. But let me go ahead and actually run this code, and we'll see what happens. We'll put a breakpoint in a couple of places, and F5 it. So here's the application again. We'll pick an image. And we hit our first breakpoint. And this is the create task of pick single file async. And because we're asking the user to do something, which is to pick an image, and we know the user is going to take more than 50 milliseconds, we make this an asynchronous task, which means that the process of actually picking the file and showing the UI happens on another thread. And then if I step over this, you'll notice that I jumped straight to the bottom. I didn't jump to that next line of code that says, what did it return null? And I actually print the last line of code first, which is a little bit confusing. So we'll hit F5. And now we get to pick the image. We'll pick Kenny's face again. Hello, Kenny.
Okay.
Now the asynchronous task is completed. We're on to another asynchronous task, which is reading the image off disk, because decoding a JPEG could take a long time, especially if it's large or if it's on a network share or something like that. And again, if I F10 over this, I jump past the next piece of code into the second debug string. We'll hit F5 again. The JPEG finishes decoding, and now I'm at the final piece of code where it creates the bitmap, adds it to the image, and outputs the final piece of text. And if you look in the output window, we'll see number 1 happened last, number 2 happened in the middle, and number 3 happened first. So it's backwards to what you might expect. And there's the finished image. So if we review this code again, we'll see that there were a bunch of different things that made it rather cumbersome to use from C++. The first one is that we had to use this create task method to actually call the asynchronous methods, which is a little bit weird. We're wrapping a method inside another method. Then we had to create some continuations using the then method and passing in a lambda. And then finally, we had to actually know the types of these things being returned. We couldn't easily use the auto keyword, which is everyone's favorite keyword in C++ these days, because why type types when the compiler knows them for you? And so all these things just make it kind of cumbersome. And it's not the way that you would expect the code to work. And there's got to be a better way, right?
Yeah,
Eric?
it can be, definitely.
Tell us.
Yeah, well, we are going to use coroutine, in this case co-wait, to improve the code. In fact, the code is trivial if it's synchronous. We just have to use the file packer. We open the file and read the file. Pretty straightforward. But with the asynchronous pattern, it can be a bit more complicated. But in this case, if I create my routine in a task, I can use co-wait to call the ping single file async. And you see not much continuation in this case. And the same for for reading the file with the co-wait. And the code look pretty simple in this case. And
that's great.
And that suggests to go on the code itself. So what I can do here, it's pick the code you use. Okay, just this part, in fact, and create the task. In fact, I have already the proto in my .h file, so that means I can create a task of void. And here I am in the async demo for build, so async demo for build namespace. Here it's main page, and my proto function is pick an image. Okay. In the code of this, I just copy the code you just used, and I will correct that guy. Okay. First of all, I don't want to create a task here, but use auto, file name, and let's see co_wait, and I can remove, of course, this part don't need anymore. So if my file is not null, it's okay. For this guy, I do the same, auto, and in this case it's stream, and I say co_wait. I can remove these guys and that. Pretty simple, no?
Yep.
Okay. Can align, and this guy no need no more. Okay.
Yeah, here's file, not file.
Oh yes, you're right.
Now we cooperatively debug.
Yeah. Thank you.
And you need the using
triple programming.
You need the using statement for Windows storage streams.
Exactly. So I have to increment this include, because I will use coroutine,
Yes,
so I
that's
have to
coroutine.
include, and it's still experimental because it's on technical specification,
Yes,
not
it's
yet on the standard.
yeah.
I will use PPL await for my task and some namespace like concurrencies, and don't forget the platform in this case. So right now it's okay. The only thing I have to do is to add a flag. So for all my configuration, I will add this flag, /await. Okay. And now I'm good to build this guy. Let's see if it's okay.
Okay, let's go.
Yeah. But I forget.
I think we forgot the curl at the end.
Yes, I forget something here. It's to comment all this code and call my new function. It's pick an image. Yes, it's better this way. Okay, run it. Okay, so exactly the same application.
Yay! Wait. Let's see if it works.
Yes.
It works.
It works with Kenny
Awesome.
image. Yeah. So in this case, we really simplify the code with few lines of code and the using of co-wait, two cases in this example. Back to the slide. Of course, we can use more complex example than this trivial one. In this case, I try to create a TCP reader. So you have to create some features, you have to create a function, and we can see here that we use the function with some features, and we call the do while and all this
Yeah,
kind
the
of stuff.
point is it's very complicated.
Yeah, yes.
You don't want to write this code.
Yeah, don't.
But you
Yes,
will prefer this
exactly.
one because
Yeah.
it's straightforward. You just connect your TCP and you read your buffer, no more. So we really enjoy using coroutine in this case. But what is the science behind the coroutine? And Go, can you explain
Eric.
that?
So, as you probably saw, that coroutines allows you to dramatically simplify your code, asynchronous code. And it's no wonder that if you see that coroutines are becoming popular, more and more languages are getting them with roughly the same syntax. So what makes C++ coroutines different from coroutines in any other languages? So one thing you probably noticed that it is purely cosmetic. In other languages, coroutines have to be marked up with some tag on the first line of the function, async. Well, I think it's async, at least in all of the examples I showed. Whereas in C++, you don't have to annotate the function at all. In fact, coroutine is a normal function from the outside. You cannot tell that it's a coroutine at all. It's only when you look at the implementation and you notice that somebody used special keywords, co_await or co_return or co_yield, that explains to a compiler that it's a coroutine and not a regular function. But again, on the outside, it's a regular function. You can put it on the ABI boundary, make it extern C or anything else. So another difference in C++ coroutines are a set of design goals we set to guide the design of the coroutines. So first of all, we wanted to make sure that the footprint of a coroutine is very small. It's just a few bytes. So if you so desire, you can create 1 billion of concurrent coroutines at the same time. And as long as the memory can fit that many. Also, we wanted to make sure that coroutines do not bring any undue overhead. So if the task at hand can be solved nicely with coroutines, you shouldn't think twice. Just go and use coroutines, because the overhead of suspension and resumption of the coroutine is comparable to an overhead of the calling a function. In fact, when coroutine is inlined, essentially it disappears. There is no overhead at all. Another one is that we wanted to make sure that, because C++, one of the properties of the C++ is that it has a very nice backward compatibility story. You can interact with C legacy libraries, we want to make sure that you can integrate coroutines on any side. So for example, because we didn't change the calling convention or the function type, the coroutine itself, you can call it from C because it's a normal function, you can put it on a DLL boundary. Also, if you are interacting with some asynchronous library written in C, you can pass coroutine as the void star context parameter, which is frequently used in those kind of APIs. And when the callback comes back to you, it will reconstitute the coroutine from that void star and being able to resume from essentially C code. Finally, we didn't want to tie coroutines to any particular libraries because we wanted to make the scope where coroutines can be used very, 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 very large. So if you are in the kernel mode, writing the drivers, you can use coroutines because they're open-ended. You as the developer or as a library developer explain to the compiler what is the semantic of the coroutine. And on the same note, we wanted to make sure that coroutines are not necessarily tied to exceptions. So if you are in an environment like kernel mode, or your company policy prevents you from using exceptions, you can use coroutines there as well. On a philosophical level, we treat coroutine as the generalized function. It's a function which has one more operations. A normal function, they have call and return, and coroutine gets one more, suspend, which allows you it suspend execution right in the middle, or maybe 20% execution, but not necessarily in the middle. And then at later point, you can resume it. But when you suspend coroutine, all of its state is preserved so that whenever you resume, you just continue from that point on. And essentially, when a user provides some code to the compiler sees if there is an await, well, it should treat it like a task. If it has core yield, it's more of a generator, which is lazily produced sequence of values. If it has both, it's a very strange beast. It's a synchronous generator, so you can use both core await and core yield in the same coroutine. And finally, if you have none, that's what we used to have before. It's a plain old function. And one would say, well, C++ language is already very complicated. So like you're adding all of that complexity. Now compiler has to be aware about tasks, generators, and other stuff. No, compiler does not care. The approach we took is that the semantic of the coroutine is fully defined by the library. Compiler performs syntactic desugaring of the coroutine, changed essentially internally into a state machine. But the semantic behind what does it mean to be, a coroutine with await is defined by the library. So if you, for some reason, don't like the PPL await adapters that Eric and Peter showed in the examples, well, you can write your own. There is no limitation. So if we look closely, what happened to the language? Well, we got 3 new keywords: core await, core yield, and core return. For those who want to customize coroutines, they need to be aware of 2 new concepts, which are requirements on types. One is awaitable, and that is what core await expects the expression to be. And the coroutine promise is for those guys who want to design new coroutine types. And 2 concrete types: coroutine handle, which represents a handle to a suspended coroutine, and coroutine traits. It's how compiler can discover the machinery which describes the semantic of the coroutine. But if it sounds somewhat complicated, don't worry, because coroutines have layered complexity. And most of the time, most of the people
like us.
will be...
Like me.
Like me, yes. Will be using just the syntax we showed, nice friend, like in other languages with core await. If you rely on coroutines and await adapters written by others, just use them as if you're in other languages which has those facilities. But if for some reason you don't like how await is interacting with a particular asynchronous facility, or if a particular library API is not covered with await at all, but you want to await on it, you can write your own. And finally, if you're adventurous, you can learn how to create new coroutine types. So C++ 17, which is next year, will not have coroutines. Just a few weeks ago, it was voted that coroutines will go into technical specifications so that there will be more field experience with them and more compiler vendors will be able to experiment with them. And we have coroutines in the latest release of Visual Studio in update 2. They are, first of all, fully supported in store apps, but you have to be aware because this feature is in experimental status. It is not part of the standard yet. So if you start using them, well, you need to be aware that there could be some little tweaks which can happen to the coroutines as they go through standardization bodies. So potentially, you might need to change your code a little bit if any of the specification of the coroutines change. But besides that, coroutines are supported. Also, there is an implementation in progress in Clang. So if you're relying on Clang, at some point soon, hopefully, you will get this kind of coroutines in Clang as well. Now, back to Eric.
Okay, back to the call to action. Very easy here. Just start using co-await and don't forget the /await on the command line flag. Give us some feedback about your experiment with coroutine. You can reach us on user voice or by tweet. Pretty easy, I think. If you want to see more about coroutine, here are two links for the session. One on meeting CPP by James. It's introductory level, and another one on CPPCon by Hugo, a bit more advanced. And of course, you can have some additional developer content on Channel 9 on Microsoft Virtual Academy, and perhaps soon a Virtual Academy on coroutine.
Sure.
Yeah, let's do that. Okay, that's it for today.
Yes, thank you.
Thank you, and bye.
Thanks for watching.